Hey everyone, welcome back. This explainer is brought to you by Forge College. Today, we're diving into scoping EVM execution analysis. Now, imagine you're a mechanic, right? You're about to tear apart a high-performance engine to make it run faster. Well, you wouldn't just start ripping out wires and loosening bolts blindly. You need a schematic. You need an engineering blueprint. And it's the exact same thing in the world of Ethereum smart contracts. Before we tear apart an execution engine to optimize gas, we absolutely must have a highly specific plan of attack. And that's exactly what we're building today.
Because, frankly, here's the harsh reality. If you jump straight into raw JSON trace data without a plan, it's just utter chaos. It's unscoped tracing. I mean, it's literally the equivalent of reading the entire English dictionary from A to Z just because you're trying to find a single typo. Or, going back to our mechanic, it's like trying to optimize a race car by just randomly unscrewing bolts and, hoping it goes faster. You'll end up completely drowning in dozens of transactions and thousands of opcode rows. And the result? Absolutely zero clear optimizations. It is just a massive waste of your time.
So, here's our master plan for today. We'll start with the blueprint concept, move into extracting traces, then spotting motifs, cover a 6-step workflow, and finally build our scope document.
Okay, Section 1, the Execution Analysis Blueprint. Let's get right into it.
Think back for a second to our previous lesson on the synthesis of opcode patterns and constraints. You already know how to identify those reoccurring opcode patterns. You've got your catalog of high-frequency sequences, but now we're taking those raw inputs and giving them a focused structure. Our ultimate goal for this capstone is to create a scope document. Think of this as a structured blueprint that links your specific EVM execution questions to measurable instruments and really strict validation checkpoints. We want to establish a highly focused scope so our flowchart highlights traceback analyses with real, tangible data, not just speculative, hey, maybe this will work suggestions. To put this into perspective, consider the difference between a weak approach and a strong one. Optimize gas. I mean, what does that even mean? How do you even know when you're done? It's way too vague. Now compare that to a scoped hypothesis. At least 40% of gas is spent on SSTORE. This is fantastic. It's a concrete target. It's totally falsifiable. We can look at the data and definitively say yes or no. And having that clear, measurable finish line is absolutely crucial.
Moving right along to Section 2, extracting opcode traces. Now that we've shifted our mindset from vague guesses to concrete hypotheses, we actually need the right tools to extract the raw data and prove those hypotheses. So how do we get this data? Well, we use what I like to call our diagnostic scanner. It's essentially just a minimal Node.js script using ethers.js to call debug_trace transaction via an RPC endpoint. It's super simple. You just pass in a transaction hash, and the Ethereum node spits out the complete, step-by-step execution trace of exactly what happened under the hood.
And inside that trace response, you're hunting for one specific array called struct logs. Let me tell you, this thing is the absolute goldmine of a Geth-style trace. It contains all the step-by-step EVM execution data. By just iterating over struct logs with a really simple loop in our script, we can tally up every single operation and build a straightforward opcode-frequency map. It lets us see exactly what the EVM was doing.
And the cool thing is, this raw data immediately tells a story. For example, if we see STSTORE happen 12 times, well, that implies storage writes are dominating our gas, so we should immediately be thinking about optimizing our storage layout or batching writes. What if KK256 triggered 18 times? No way! Hash and costs are bleeding us dry here, so we need to examine our indexing schemes. And 7 accals? That tells us cross-contract overhead is definitely a factor. You see, this early validation checkpoint quickly reveals if a transaction actually exhibits the hotspots we expect, way before we spend hours analyzing it.
All right, Section 3, spotting high-cost motifs. Let's zoom in a bit closer.
Once we know the overall frequency of our opcodes, we need to find the specific microfractures in our machine where the gas is leaking out. And the magic number here is 3. Now, why 3? Well, when we're looking for patterns in the EVM, 3 opcode contiguous sequences strike the absolute perfect balance. They offer just enough locality to capture immediate instruction neighborhoods where small refactors can happen, but they're short enough to actually repeat as identifiable patterns across all our transaction traces.
So, to actually find these motifs, we write another small script. We parse our trusty struct logs, but this time we map each opcode to a static gas cost. We group them into chunks of 3, sum up their gas costs, and we rank them. The 3 opcode sequences that rise to the top of this list and repeat across multiple traces are our prime suspects.
They basically become the absolute best candidates for the nodes in our final capstone flowchart.
Which brings us to Section 4, the 6-step scoping workflow. Now that we have our diagnostic scripts ready to pull frequencies and rank sequences, we need a solid framework. We need to tie all these technical scripts into a repeatable scientific experiment. So here's our plan of attack. Step 1. Select your surface area. Step 2. Formulate 2 to 6 falsifiable hypotheses. Step 3. Define your success criteria and instruments. Step 4. Sample and validate. Step 5. Plan your optimization strategies. And finally, Step 6. Set hard acceptance checkpoints. This disciplined workflow is exactly what prevents you from wasting like 3 weeks trying to optimize some micro pattern that saves exactly $0.
Actually, let's pause and place a massive emphasis on Step 4 for a second. When you pull your early sample of just 3 to 6 transactions, you have to honestly ask yourself, do these sample traces actually exhibit the suspected hotspots? Look, if you hypothesized a massive hashing bottleneck, but Kekek256 barely even shows up in the struct logs, stop. Seriously, don't force it. If the sample doesn't support the hypothesis, it is time to quickly pivot your scope to where the data is actually pointing.
But once you've successfully validated your hotspots, that's when Step 5 kicks in. The specific opcode profile you just discovered dictates exactly which optimization strategy families you're going to pursue. If SSTORE is out of control, well, you look at storage optimizations like packing structs. If calls are dominating the trace, you look at call structure optimizations like inlining. Or if hashing and math are eating all your gas, you look at algorithmic changes like pre-computing values off-chain. Let the data make the decisions for you.
Section 5, the scope document. Everything we've discussed so far funnels right into this.
This is the main artifact you must produce before picking up your virtual wrenches. Your personal scope document template is super straightforward and it maps directly to your final capstone flowchart. You simply list out your target method, your testable hypothesis, the metric you're tracking, the measurement method, a strict checkpoint, and your initial candidate strategies based on the data.
The beauty here is that every single claim in your blueprint must be tied to a concrete measurement and a strict checkpoint. Let's say your metric is gas percentage from SSTORE. Your measurement method is computing gas per opcode from struct logs, and the checkpoint, accept only if it's greater than 35% in at least 3 out of 5 sampled traces. Or, what if your metric is average call depth? You track call and delegate call occurrences and accept it only if the average depth is greater than 2 from most traces. It leaves absolutely zero room for ambiguity. You either hit the checkpoint or you rethink your scope. Simple as that.
All right, Section 6, next steps and conclusion. We've built the blueprint, so let's set the stage for the actual trace annotation.
Your immediate next step is to prepare for our upcoming phase, tracing execution with examples. So here's what I want you to do. Run your Node.js summary scripts. Gather 3 to 6 representative transaction traces and generate those JSON opcode summaries. Make sure to save all those output files in one dedicated folder because we are going to need them immediately in the next lesson.
So I'll leave you with this provocative thought. What hidden gas leaks will your blueprint reveal? By forcing yourself to establish a really clear scope, you eliminate the noise, you eliminate all that ambiguity, and you focus only on what mathematically matters. I really hope you found this breakdown incredibly helpful and hey, maybe even a little fun. Remember, this explainer was brought to you by Forge College. If you want to master more Web3 engineering topics and dive even deeper into the EVM, please visit forge.college. Thanks for hanging out with me and happy scoping.